On the opposite side, it says rank these from most positive to most negative, the electric field at point P. Take the positive direction to be to the right. We basically just did it because we stuck the same charge every time at point P. So the ranking is going to be the same, but there's one difference. This time we're taking direction into account. Last time we didn't. We just looked at magnitude last time. So the ranking will be a little different. The only thing that's not going to change, which two are going to be the same? A and F are still 0. And then which ones split? So B and G are next, right? B would point to the left, is that correct? And G would point to the right. So that means G was positive and B is negative. And D and E, D points to the right, E points to the left. And C is to the left, isn't it? So all of these on this side points in the negative direction. And those, the E points in the positive direction. Okay, electric field, electric force. What do you think is coming next? Electric potential. Rank the electric potential from most positive to most negative. What's the electric potential for F? Situation F. The one where the electric field's 0 at that location. It's tempting, isn't it, to say 0. How do you find the electric field from a point charge? Let's just say there was only one point charge there. Cover one up with your hand. Only one point charge there. What would be the electric potential at the X? Point marked with the X. KQ over R, right. Now uncover the other one and cover up the first one. What would be the electric potential due to the other charge at that location? KQ over R. Now take your both hands away. You got 2 point charges there. What's the potential at the center? Two KQ over R. See, you're so brainwashed into doing vector addition. Electric potential is not a vector quantity. You just add them up. In this case, if they're both positive charges, they're both creating positive potential, you just add them up. And you get twice as much. F was, what was F? Positive. Now let's do C. What do you think it's going to be? 0, because it's the potential from the negative charge plus the potential from the positive charge. Negative, well, let me write it this way. It's K negative Q over R plus KQ positive Q, right, over R. So which one is our most positive? Let's rank them. F is the most positive. A is the most negative. There's a 0 somewhere. C is 0. And what else do we have? G is going to be slightly positive. And then D is a little more positive. B is slightly negative. And E is more negative. And A is the most negative. Okay, we agree with that? All right, so this is key point here, right? You do the electric fields, they might cancel out because they're a vector quantity. and you get a zero electric field between two like charges, between two like charges, they definitely cancel out. But the potential adds. You get twice the potential at that location due to the two charges. You just add them up. Just add them up. Okay, have we done electric potential energy? The third one says, find the electric potential energy of the system of three charges if a positive Q is placed at point P. Electric potential energy. Different from electric potential. And how do we get the electric potential energy? We multiply by Q, by the Q that we're sticking there. So the electric potential energy is Q times the potential. And that comes from the work done. Also, we can use the equation for work done. Because it comes from the same thing. If we have to do work, if we have a positive charge out at infinity and another positive charge at infinity, and we bring them together, they want to repel each other. So as we bring them closer and closer together, we're doing work on them. And we get to a certain point and we stop. We've done a certain amount of work bringing them in. And that's how much energy is stored in that system. And we let go of them, and they move back out to infinity, and they would have a certain amount of kinetic energy at the end equal to the original amount of potential energy that they had, equal to the work done that we did bringing them together. Yeah.
So we're using Q here a lot. Which charge are we talking about here?
This is the charge. This is the one that we're putting at point P.
Okay. And in potential, we're using the other charge.
Due to all the other charges, yeah. It's actually this is this is due to an existing charge. This is for two charges. That's the electric potential energy for two charges. It's the potential created by the first charge multiplied by the second charge that you bring in. Okay? And the reason we do it this way is that the first charge, it doesn't take, if you have two charges infinitely far apart, bringing the first charge in doesn't take any work, right? There's no electric field, we're not fighting anything. Then when we bring the second charge in from infinity, we're doing work against the first charge. And so then there's stored energy in that system. And it could be positive work, meaning that we're bringing in two like charges, they repel each other, we're doing positive work to assemble that system. Or it could be negative work, it could be opposites. They might want to attract, and we have to hold back and pull back to get them in, because we want them, eventually we want them at rest, right? So they want to speed up as they come in if they're attracting each other, and we'd have to pull out, do negative work on the system to bring it to rest to get them to that point.
So then is it a vector quantity?
No, energy is not a vector quantity. But potential energy could be positive or negative. We did that with gravitational potential energy also, right? Because your zero is arbitrary. If I'm dropping something, I might say, well, I'm going to make my desk, that's the lowest point that the pen can hit. I'm going to make that 0 height and call this some arbitrary, measured against 0, its potential energy. You might say, well, I'm going to call the floor 0, and it's going to have more potential energy, but they both have the same delta. Or when we did, I don't know if you did it, but sometimes in lab, we'll measure the distance that a weight drops and how fast the cart's moving. There's a lab we do like that. And we'll set up an equation to see if the energy, if the sum of the potential energy of the weight as it drops and the kinetic energy of the cart plus the weight as they move are equal to each other as time goes on. And it's easier in that case to call the starting height 0 of the weight. And as it drops, it has to go lower than 0, so we call it negative. So it starts at 0 and it goes negative. That's okay too, right? As long as it goes down when the weight gets closer to the center of the Earth. So in this case, we could have positive or negative potential energy. So let's just do two charges. We have we've got a plus Q1 and whatever, plus Q2 and a distance R12. Then the potential energy is KQ1 over R12. That's the potential due to Q1, and we multiply that by Q2. Now let's do three charges. Make that one positive, and that one positive, and then we'll bring in a third one minus. And this is R12, R23, R13. So what do? We say we're bringing Q1. It doesn't cost us any work. We bring in Q2. We have to do work against 1, right? So we get this term, we get the potential energy between 1 and 2. Then we bring in 3. And 3 is going to have two terms. It's going to have a term with charge 1 and a potential energy between charge 2. So we end up with these three values. So this first one is K, Q1, Q2 over R12. And I said they're both, okay, positive. And then this is going to be K, Q1, Q3. And if that's negative, you have to put a negative sign in there over the distance between them. And then we've got a K, Q2, Q3, and Q3 might be negative over R, oops, that should be 2, 3. So you could actually end up with 0. Maybe you've got two positives and a negative, and you have to retain the signs. Be very careful with the signs. Some of these terms are going to be positive, some are negative. You might end up with 0. Maybe it costs no energy bringing them in because some of them you did positive work, some of you did negative work. It might, by chance, sum out to 0. And then you just add them up, right? It's a scalar quantity. Just add them up. All right, so we don't have to do it for this one, but you've got the idea, right? You've got two charges plus a third. So you're going to be using this formula here. And you can do it for the different configurations.